All right, here we're talking about reference frames and the fact that velocity is relative. I want to first consider a coordinate system that is fixed to the Earth. And if we have this truck and it is moving with respect to the Earth, then the person standing in the truck is also moving with respect to the Earth. So if I were to draw a position vector, r, for that person, that position vector will be changing with time, right? If we've got, our initial here, and then we take that truck and we allow it to move. There we go. We allow it to move. So that would be my R initial, and then my R final would be over here. Okay, see if I can fix that. My R final vector would be over here, and it's pretty clear that R is changing, so the person has a velocity. And in fact, the velocity of the person is the same as the velocity of the truck. Okay, and that makes sense. Okay, we've got an object that's moving, and so it has a velocity. However, what I want to show us is that we can create a different coordinate system. We can create a coordinate system that is fixed to the truck. Maybe call this x prime and y prime. And since the coordinate system is moving with the truck, when we draw the r vector for this person, r initial and r final, they're the same. The person has not moved. So the velocity of that person in the blue coordinate system, or the primed coordinate system, is 0. So we could say v prime here is equal to 0. He's not moving in a coordinate system that is fixed to the truck. And so, which one is real? Which one is his real velocity? And the answer is, you might say the answer is, the real velocity is the one measured in the red coordinate system because the truck's moving. But have you considered that the Earth is also moving? The Earth is spinning, and it's going around the sun. It's actually moving really fast. So how fast is the person really moving? Have you considered that the sun is also moving as it rotates around our galaxy? So how fast is the person really moving? Or have you considered that our galaxy is moving throughout the universe? So how fast is the person really moving? And the answer is there's no such thing as how fast he's really moving. Velocity is always measured in a coordinate system. So we have to define a coordinate system before we can decide how fast an object is moving. So in this blue coordinate system that's moving with the truck, this person has a velocity of 0. In the red coordinate system that's moving with the Earth, the person has a velocity of, let's say 30 meters per second. So his velocity depends on his coordinate system. Now, what's really interesting then is if we have two different coordinate systems, how can we compare the two velocities? So let's say instead of standing still in the truck, let's say that he's actually moving in the truck. Maybe he's moving at 3 meters per second inside the truck. And so his velocity inside the truck is 3 meters per second. So what that means, sorry about that, every once in a while I click my iPad and the whole thing like scrolls forever, and I don't know why. Why is that happening? Okay, so if he's moving inside the truck, and I don't want to make him headless. If he's moving inside the truck, then of course his position inside the truck is going to change. That means he's going to have a different R final. Well, it did the thing again where it jumps. My Apple Pencil is acting up, I think. It's got enough charge. Okay, so the point is, now he's moving inside that truck, and so now his if we know how fast he's moving inside the truck, maybe we'd like to also know how fast he's moving across the Earth. And I think you can figure this out. How fast do you think he's moving across the Earth? If the truck's moving 30 meters per second and he's moving 3 meters per second inside the truck, how fast is he moving across the Earth? I think you can figure that out. Probably 33 meters per second. Okay. My Apple Pencil is starting to really act up. Let me see if I can fix this quickly. And if I can, that's great. And if I can't fix it quickly, I will start a new video. Let's give this a try. All right, I think that's going to be okay. Okay, I was saying that the velocity measured with respect to the Earth is going to be 33 meters per second. Okay, and that's true if he's walking forward at 3 meters per second, but what if he was walking backwards at 3 meters per second? If he's walking backwards at 3 meters per second, then his velocity with respect to the Earth would be 27 meters per second. And I hope that seems kind of obvious. And what we're getting at is a general principle that says your velocity, let's say, of the person with respect to the Earth, okay, my pencil is still acting very badly, is equal to the velocity of the person with respect to the truck plus the velocity of the truck with respect to the Earth. And since these are both vectors, we have to add them like vectors. Okay, and this is the equation for relative velocity, and it doesn't have to be a person in a truck. It can be any object and any two coordinate systems. So this would be like the first coordinate system, the Earth, and then the truck would be the second coordinate system. And you see that the velocity of the person with respect to the Earth is equal to the velocity of the person with respect to the truck plus the velocity of that second coordinate system, in this case the blue coordinate system, with respect to the red coordinate system. All right, I'm going to try to see what's wrong with my pencil, and I will come back with an example.